In this section, we discuss the phenomenon of total internal reflection. When light passes from a medium of larger refractive index into one of smaller refractive index, for example, from water to air as shown here, the refracted ray bends away from the normal. If the angle of incidence increases, so does the angle of refraction, and it will continue to increase until the angle of incidence reaches a certain value, called the critical angle, theta c, where the angle of refraction is equal to 90 degrees. In this case, the refracted ray points along the surface. We can obtain an expression for the critical angle, theta c, from Snell's law by setting the angle of refraction to 90 degrees. In this case, we have sine theta c equals n2 divided by n1 times the sine of 90 degrees, or sine theta c equals n2 divided by n1. Note that this is only valid for n1 greater than n2, since the sine of an angle cannot be greater than 1. This means that we can only calculate an angle of total internal reflection for the case when the light travels from a medium of higher index to a medium of lower index. This makes intuitive sense as well, considering that the light bends towards the normal for the case in which light travels from a medium of lower to a higher index of refraction. This would mean that, even if the incident light were parallel to the surface, the refracted beam would be bent towards the normal and hence could never be parallel to the surface, and total reflection would not be possible. Therefore, the term internal in total internal reflection refers to the incident light being inside the medium of larger index of refraction. The critical angle, theta c, represents the minimum angle for which total internal reflection will occur. This means that total internal reflection will occur at angles equal to or larger than theta c. An important application of total internal reflection occurs in fiber optics, where thin threads of glass or plastic, called optical fibers, pipe light from one place to another. Here we show a typical optical fiber that consists of a cylindrical inner core that carries the light and an outer concentric shell called the cladding. The core is made from transparent glass or plastic that has a relatively high index of refraction. The cladding is also made of glass, but of a type that has a relatively low index of refraction. Light enters one end of the core, strikes the core cladding interface at an angle of incidence greater than the critical angle, as shown here, and is therefore reflected back into the core. Light thus travels inside the optical fiber along a zigzag path. In a well-designed fiber, very little light is lost as a result of absorption by the core, so light can travel many kilometers before its intensity diminishes appreciably. Optical fibers are often bundled together to produce cables. Because the fibers themselves are so thin, the cables are relatively small and flexible and can fit into places inaccessible to metal wires. Also, due to their compact size and flexibility, optical fibers are often used in medical applications such as robotic surgery, where imaging in tight places might otherwise be impossible.